Hello everybody. So in this video, this is going to be the first video where we actually talk about solving differential equations. So why would we want to solve a differential equation? Well, solving a differential equation means we're finding a model to describe a physical phenomenon. So for instance, very basic thing that people were thinking about hundreds of years ago, maybe thousands, is how do you describe the motion of an object that you toss into the air? If I toss this into the air, right, it goes up and it comes down, yeah, but I think we can do a better job of explaining that. In fact, I think we know a little, we know that it goes up and slows down and then comes back down, and so we might want to find a precise model that describes exactly the motion. And then we can use such models to predict what's going to happen if we throw something at a certain rate from a certain position. Where is it going to end up? How hard do I have to throw it? How fast do we have to shoot it to get it to go where we want it to go? Okay. So let's do this today. All right, so let's go down to the sheet. And let me remind you of what we were talking about in the last video. In the last video, we talked about some basic concepts of differential equations. We talked about what a differential equation is, what the order of a differential equation means, and how to verify whether something is a solution to a differential equation. And like I said, today we're going to talk about solving differential equations. Now we're going to talk about solving differential equations of a certain form. And as the course goes on, we're going to learn how to solve more complicated differential equations. But today we're going to look at differential equations like this. So let me talk a little bit more about this. Recall in the last video, we mentioned that the differential equations we're going to be looking at in this class are all going to have this form. The nth derivative of y is going to be expressible as a function of x and the lower derivatives of y. So it's a function of x, y, y prime, y double prime, all the way up to the n minus first derivative of y. So these are the differential equations we're dealing with in this class. Today, we are going to look at an even simpler case where the function actually only depends on x. So you could think of it as a function of all these things, but it just doesn't depend on them. We can think of it as a function of x alone. And these differential equations, turns out, we can solve pretty easily just by using techniques from calculus. Okay? So let's look at a simple differential equation of that form. Okay? Y prime equals x. So it's a first order differential equation, n is 1, and the function of x is just x itself. Okay? So to find the solution to this, well, let's just think about what we know from calculus. In calculus, we know that if we know the derivative of something, we learned how to find that something by computing an antiderivative. So if y prime is equal to x, well, we know that y is an antiderivative of x, and that amounts to taking an integral. Well, what does that integral become? 1/2 x squared plus c. What is c? C is any constant. Because if I put any constant here, and I take the derivative, well, it becomes 0. And then when I take the derivative of this, it becomes x. So I do get to this. And this can be any number. So let me just write that, where c is any constant. Sometimes they call it an arbitrary constant. Same thing. Okay, so we've solved the differential equation. There you go. Okay. Now let me show you another way that the differential equation might be presented up front. Instead of simply writing y prime equals x, you might be told that some more information here. You might be told that y prime equals x, and moreover, y of 1 is equal to 3. So we're given some additional information. Well, how would we solve this? Well, I'm starting with the same thing, y prime equals x, so I'm going to get the same solution. All right, so what this gives me is y equals 1/2 x squared plus c, where c is any constant. But now we can use this additional information. What happens when we use this? Well, this information is saying, so let me explain this notation. When I write parentheses in a number, I'm thinking of y as a function of x. So this is the value of x in here. When x is 1, y is 3. Well, let's just put that in here. Y is 3 when x is 1. Look at this. This is an equation that I can solve for c, right? This is 3 equals 1/2 plus c. So subtracting 1/2 from both sides tells me that c is equal to 5/2. And so in this particular case, I've solved for the constant. So I can write down my solution in a more specific form. I can write my solution as 1/2 x squared, not plus any constant, but plus, it has to be this constant. That's the only way I'm going to get this to happen. Y of 1 equals 3. And so there is my solution. So notice, if you're given a differential equation without any other conditions on it, you're going to write the solution in terms of arbitrary constants. If you're given other conditions, you might be able to find what those constants are. You're usually going to be able to do that, and if you can, you should. So find those constants, and then write out your differential equation in the final form with those values in place of those constants. Okay? All right, let's do another differential equation. Let's look at something like y double prime equals cosine x. Okay, so here I have a second order differential equation is a function of x. Sorry, a second order differential equation where y double prime is a function of x. Well, I can do the same thing here. I can start getting rid of derivatives by anti-differentiating. So if I anti-differentiate once, I go from y double prime to y prime. And if we simplify this, if we evaluate this indefinite integral, we see we get this. So this is a new equation for y prime. And now we have a first order differential equation, so we can now find y by anti-differentiating again. Okay. Find the antiderivative of sine is negative cosine. And I get another constant. I'm not going to write where c and b are arbitrary constants. Let's just understand that that's what we mean here. So I've solved this differential equation. All right. So let's look at this same differential equation with some initial conditions. All right. Let's say that y of 0 equals, I don't know, 5, and y prime of, let's say, let's do something interesting like pi over 2 equals 8. Okay? So we have our differential equation and two conditions along with it. So I know that when I solve this differential equation, I get this. Okay? Just doing exactly what we did before. But now how can we use these initial conditions to figure out what C and B are? Well, let's also look back and see what we had up here. We also had, well, I don't have to write it again, I'll just look at it up here. Y prime is equal to sine x plus C. Now I'm told that y prime of pi over 2 is equal to 8. So if I take this differential equation up here, right, and use this, what do I get? Well, I'm told that y prime is 8 when x is pi over 2. Well, what's sine of pi over 2? Sine of pi over 2 is 1. So 8 equals 1 plus c. Therefore, c is equal to 7. So we've solved for c. Fantastic. Let me write that over here. So now we know that y is this. We've figured out what c is. Now let's figure out what b is. Well, for that one, we're going to use this other condition, y of 0 equals 5. In other words, when x is 0, y is 5. So let me put 5 in place of y and 0 in place of x. Now let's see what we get here. 5 equals negative 1 plus b. So that tells us that b is equal to 6. And so I've solved it with those conditions. There's my solution. So notice what we have here. If you aren't given conditions, then when you solve the differential equation, you'll solve it in terms of constants. If you do have conditions, you can try to solve those constants, solve for those constants, and write down the solution without any constants. Okay. Now let me just show you one other thing that could happen here. What if I had y double prime equals cosine x, and only that other condition, let's just say y of 0 equals 5. Well, if I only had this, then I could only do, well, I'll start with my solution I know in general. The general solution in terms of these constants is this. All I can do is plug this stuff in. So I know that 5 equals negative cosine of 0 plus c times 0 plus b, right? And so I know that b, all this stuff is 0, so I know that b is equal to 5. But that's the best I can do, right? And so my final answer is still going to be written in terms of a constant, right? There's still a constant left over. I can't solve for that. So depending on how many initial conditions you have and what the order of your differential equation it'll determine how many of these constants you can actually solve for. Okay? Now let's go back to that original problem that we talked about at the beginning. We talked about throwing an object into the air. How do we model that motion? Well, let's just think about this physical situation. If I throw an object into the air, what is determining its motion? What do we know that's certain about its motion? Well, we know that near the surface of the Earth, the acceleration due to gravity is constant. Right? There's a constant acceleration. And you can go look that up, and you'll find that it's exactly 9.8 meters per second squared. Now, how does acceleration relate to the height of the object? Well, acceleration is the second derivative of position. And here we're representing the position as a height. So this is our differential equation. Our differential equation is the second derivative of our height is negative 9.8 meters per second squared. This is our differential equation. I put a negative because height we think of as upwards as being positive, right? And the acceleration is going downwards. So it's going against the upwards direction. So I put a negative here. Let me, instead of writing negative 9.8, let me just substitute a letter temporarily, okay? So I'm going to write y double prime equals a. So we just have a differential equation where y double prime is a constant. That's all we have to do to model the motion of objects thrown into the air. So let's go ahead and solve this. If y double prime equals a, that means that y prime is the antiderivative of a. Now I'm not thinking of, I'm gonna write a t instead of x because I'm thinking of this as a function of time, and so let's use the letter t. You could use x, but let's use t this time. All right, so y prime is equal to at plus b. And now I can find y. Y is the antiderivative of y prime, so it's the antiderivative of at plus b. So that's 1/2 at squared plus bt plus another constant, c. And if you've taken a physics class, this should look very familiar to you. This is exactly how you model the motion of an object thrown into the air, and it all comes from this differential equation here. Now, you might be told that you throw the object into air from a particular height. Let's suppose that the initial height is 1 meter. And let's suppose that the initial velocity that we impose on this is 3 meters per second. Can we figure out what these constants are? Well, we can try. We already know what A is. A is negative 9.8. We just have to find B and C. Okay, so let me go ahead and rewrite Y. Well, let's just let's think about this again. So what is h of 0? What's h sub 0? That's the initial height. That's y of 0. So we're being told that y of 0 is 1. And what's v of 0? V0. V0 is the initial velocity. How do you measure velocity? It's the derivative of the position. So that's y prime of 0. So we're really being told here that the initial position is y of 0 is 1 and y prime of 0 is 3. Okay? So let's take this y prime of 0 equals 3 and plug it into this equation. What do I get? Well, y prime of 0 is 3, so in place of y prime I'm putting 3, and in place of t I'm putting 0. Oops, that's an a times 0 plus b. So that tells me that b is equal to 3. All right. Now, let's go down to our other equation here for y and use this. If y of 0 is 1, that tells me that 1 is equal to 1/2 a 0 squared plus b times 0 plus c. So therefore, c is equal to 1. And so I've modeled this exactly. This model gives me, let's go ahead and plug in a. A was negative 9.8, so 1/2 of that is negative 4.9 t squared. B was 3, and C was 1. So if I throw an object into the air from an initial height of 1 meter and an initial speed of 3 meters per second, this models exactly the motion of that object. And I just want to point out that just some other observations here. What kind of function is this? Well, it's a quadratic function. It's a second-degree polynomial. So let's just draw its graph. When I plug in 0 for t, I get 1. So I know it crosses here at 1. And I know it's a quadratic with a negative leading coefficient, so I know it's the shape of a parabola opening downwards. So the object is going to go up into the air and then come back down. It's going to follow the shape of a parabola, which is exactly what we were seeing. As I throw it into the air, it goes up, slows down, and then comes back down. Now the actual motion is vertical, right? Why do we get a parabola here? Well, it's because t is our horizontal axis, so that's kind of spreading it out over time, and that's making a parabola. But this is modeling exactly what we observed, and this is how we come up with this physics equation. All right, I hope that was helpful, solving differential equations. I will see you in the next video.